Sir, your mic is muted.
Okay, can you hear me now?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
I'm not sure at what point my mic got muted, but I hope you heard the part where I said that the practice assignment will be available for you today at 6:30 p.m. and it's due by 9:30 p.m. This is not going to count towards your grade, but it's just for us to check that the process of offering an assignment and collecting your responses is okay. That was the only announcement I made. Okay, so today we will continue this discussion. In particular, I am going to talk about the Gram-Schmidt orthonormalization process. And then we'll talk about determinants.
Sir?
Yeah, please go ahead.
Sir, does the homework need to be submitted?
Yes, yeah, definitely.
Sir, till when?
Sir, I think he got confused with homework and the assignment that you're talking about.
Okay, so the homeworks are not due. Okay, you don't have to turn them in. You have to try them on your own. But as I mentioned, the assignment is actually going to be based on your homework. Typically, we'll essentially pick one of the problems in the homework or maybe two of the problems in the homework, and that will be your assignment. That is the reason why 3 hours is plenty of time for you to actually submit your assignment, because if you've already tried your homework and you already have the solutions to the homework problems written out somewhere, it's just a matter of copying it out neatly and then scanning it and uploading it as your assignment. Okay, 3 hours is actually much more than enough, but just in case some of you have internet connectivity issues and so on, that is why there is this margin of 3 hours. But yeah, I think beyond this, we won't accept late homeworks. Okay, so you have to make sure that you submit it by 9:30 every day on the day it is assigned.
Thank you, sir.
Okay, so
Sir,
but
by
before
8,
I proceed,
not 10:30. It's from 5 to 8 on Monday.
no, somebody complained that they have a class from 5 to 6:30. So 6:30 to 9:30. So we'll follow
Okay.
6:30 to 9:30 p.m. But I won't be able to push it any beyond this because it'll just be brutal on the rest of you. So I would suggest that those who have classes in the evenings have to somehow manage to do this within this time.
Okay, thank you.
Okay, so there's one definition I want to put down before I begin. This is the definition of an orthonormal or orthogonal basis. So if you are given a basis consisting of vectors v1 through vn, of a vector space V is said to be an orthogonal basis with respect to an inner product. So in order to say whether a pair of vectors is orthogonal or not, you need to have some notion of an inner product, and I denote that inner product by these braces with two arguments here and a comma between them. If this set V1 to Vn is an orthogonal set. What is an orthogonal set? We defined it in the previous class. A set of vectors are said to be orthogonal or mutually orthogonal if the inner product between any pair of vectors in that set is equal to 0. And we say that this basis is an orthonormal basis if it is orthogonal and Vi inner product with Vi equals 1 for all I. Okay, that's one definition. So two keywords that have come here: orthogonal basis and an orthonormal basis. Okay, so it turns out that any vector space V and inner product defined like this has an orthonormal basis. So the question is, how do you find such an orthonormal basis? So if you're given a basis for a vector space, then you can use the Gram-Schmidt process or the Gram-Schmidt algorithm to find an orthonormal basis for the vector space V. And why are we interested in orthonormal basis will be clear as we go further in the discussion. So the Gram-Schmidt process. Or algo. So basically this is the input. So it's a set of vectors, say x1 through xn. And these are linearly independent vectors in C to the m. And what is going to be the output of this algorithm is a set of vectors z1 through zn. Is an orthonormal set of vectors such that span of this first set of vectors or z1 through zn is equal to the span of x1 through xn. So by the way, actually the correct way of writing a sequence is always like this. You have to always write out the first two elements and then separated by a comma, then a comma and exactly 3 dots, then a comma and then the last element of the set xn. You should not put 4 dots, 5 dots and so on, and there should be always these commas in between them. And you should always list the first two. But sometimes, as usual, I get lazy and I just write z1 to zn, where there is no confusion that I'm not skipping anything in between. It's just z1, z2 up to zn. Okay, so this is how the procedure works. And I'll first put down the procedure and then maybe make some remarks as to why this procedure will yield a set of orthonormal vectors such that the span of these vectors is exactly the same as the span of x1 through xn. So I expect that you also seen this procedure previously. So this is more of a recap. So are there anybody in the class who has never heard of the Gram-Schmidt process?
Yes, sir.
Yes, sir.
Okay, so who said yes?
Me, Akil.
Akhil, okay. And who's the other person?
Sanjana.
So there are a bunch of
Sanjana,
people
okay.
raising their hands right now. So I think that it's not visible to you.
Okay, so if you've raised your hand, you can speak. So is it all the people who've raised your hands?
Like 11 or 12 people.
Yes, sir.
So all of these people have never um, heard of the Gram-Schmidt process. Is that correct?
Yes.
Yes, sir.
Okay, so now you get to see what it is. It's pretty simple. Um, you start out by saying let y1 be equal to x1 itself, and then you normalize it. So you set z1. So I've already found out what z1 is, the first vector. This is going to be y1 divided by inner product of y1 with itself power half. So this means that z1 is now normalized. I already mentioned this in the previous class. If you take any vector divided by the square root of the inner product of that vector with itself, you will get a unit norm vector pointing in the same direction as the original vector. So z1 is now normalized. Okay, now I want to find a z2 which is orthogonal to z1, but span of z1, z2 will be span of x1, x2. So how do we do that? So we let y2 be equal to x2 minus some scaled version of z1, and the scaling factor is the inner product between x2 and z1. So now what this means is that this y2 is perpendicular to z1. Why is that true? So if I take the inner product between y2 and z1, that will be the inner product between x2 and z1. Inner products are linear, okay? So it's the inner product between x2 and z1 minus this coefficient times the inner product of z1 with itself. But z1 is already unit norm. And therefore the inner product of z1 with itself is 1. So it's the inner product of x2 with z1 minus the inner product of x2 with z1, which is 0. So y2 is a vector that is perpendicular to z1. And then I normalize this and I set z2 equal to y2 divided by the inner product between y2 and itself power half. So now z2 is unit norm. And so on. So I proceed like this. And so just to kind of make it clear, in the kth step, I let yk equal to xk minus the inner product between xk zk minus 1 times zk minus 1 minus the inner product between xk and zk minus 2 zk minus 2 and so on. Inner product between xk and z1 times z1. So what this means then is that yk will be perpendicular to all the previous vectors, z1, z2, up to zk minus 1. And so we can set zk equal to yk divided by inner product of yk with itself power half. Okay, so this is the overall algorithm, and you keep going up to k equal to n.
Sir,
Yeah.
so can we say that orthogonal vectors are linearly independent?
Yeah, so if you remember in one of the previous classes, I did say that any set of non-zero orthogonal vectors are linearly independent. And I said you should try to write out a little proof for why that should be the case. Okay, so obviously if I take the zero vector is orthogonal to every other vector. Okay, you take the inner product of the zero vector with any other vector, you will always get zero. So orthogonal vectors are not necessarily linearly independent, but non-zero orthogonal vectors are linearly independent. Okay.
Yes, sir.
So, so just to make some remarks about this, just by construction, at step K, we have that span of z1 through zk, zk equals span of x1 through xk. And this is true for k equal to 1, 2, and so on. So at every k, this is actually true. So what this means is that if I want to write a linear relationship between x and z, then I can write this matrix Z whose columns are z1, z2, and so on. This is equal to the matrix X times R, where R is an upper triangular matrix. So going forward, I'll use this notation to write upper triangular in short. Okay, so if you look at this, so if R is upper triangular, what it means is that when I multiply, so just for the sake of completeness, I'll say here, Z is this matrix formed by Z1 through Zn, and X is the matrix formed by X1 through Xn. I don't want to put commas here. It's just stacking these next to each other. Okay, so if R is upper triangular, it means that if I look at the first column, remember I talked about how to view matrix multiplication. If I look at the first column of V, it's a linear combination involving only the first column of X. So basically that is what is captured by this equation here. If I take the second column of Z, it's a linear combination of the first two columns of X. Okay, and so it goes. And the second remark I want to make is that if x1 through xn are linearly dependent, remember I presented the algorithm by assuming that x1 to xn are linearly independent vectors in C to the m, but I can actually run this algorithm even if these vectors are linearly dependent. So if x1 through xn are linearly dependent, if they are linearly dependent, we can still use Gram-Schmidt. To find a basis and the dimension of span x1 through xn. So basically how this happens is that if, for example, xk is linearly dependent on x1 through xk minus 1, then when you run this Gram-Schmidt process and if you compute this yk here, it will turn out that yk will become equal to 0. So that is something you should convince yourself about. I'll write it down for you, and you should again try to write out a small proof for that. Then what you can do is to skip xk and then proceed. So you just don't compute as zk. You skip the kth z and then you proceed with yk plus 1, and then you run the algorithm. So basically this is something you should show. If xk is linearly dependent on x1 through xk minus 1, then yk equals 0. So at the end of the Gram-Schmidt process, you will have an orthonormal basis for span of x1 to xn. So to be more clear,
I think there is a noise coming from.
I'm not hearing too much background noise, but yes, there is some noise around here. I can't do much about it. Okay, these are two remarks. Okay, any questions about the Gram-Schmidt process? Okay, so I'll make one other small remark. This is it relates back to some things we discussed in the previous class, actually 2 classes ago. So this is about it's a note about orthogonal complement subspaces. Okay, so recall that the range space of A is the orthogonal complement of the null space of A transpose. So that means that Ax equals B. If I take this system of linear equations, this has a solution if and only if so this will have a solution only if and only if B lies in the range space of A. If B is not in the range space of A, then it will not have a solution. So if B lies in the range space of A, it means that B must be orthogonal to any vector that lies in the null space of A transpose, because the null space of A transpose is the orthogonal complement of the range space of A. So that so to put that in words, the way to write it is B transpose Z must be equal to 0 for any vector belonging to the null space of any A transpose. Okay, that is to say that for any Z such that A transpose Z equals 0. Okay, so that's just a side remark I wanted to make about orthogonal complement subspaces. Now there are a couple of points I want to make, and then I will state one proposition. So so consider did somebody have a question? Was there a question? So I'm defining an orthonormal square matrix. Yeah, go ahead. I cannot understand what you're saying. No, it's not at all clear. Maybe you can type out your question and Chirag or Nagbhushan can read it out. So meanwhile, I'll proceed. Yeah, I cannot follow you at all. Sorry, I cannot follow you at all. So maybe you have to type out your question. Okay, so let's consider an orthonormal square matrix. This is a matrix such that it has orthogonal and unit norm columns. That's the definition of an orthonormal matrix. And it has the property that, or another way to define it is the matrix Q satisfies Q transpose Q equals Q transpose equals the identity matrix. So by the way, in general, it's always true that for square matrices, if AB equals the identity matrix, then BA is also equal to the identity matrix. Okay, this is easy to see. Basically, if BA is not equal to the identity matrix, then BA minus I is non-zero, which implies now if I pre-multiply by A, then ABA minus A is not equal to 0, but AB is equal to the identity matrix, so which implies A minus A is not equal to 0, which is a contradiction. Okay, so for square matrices, it's always true that if AB equals I, then BA equals I. Therefore, if I say Q transpose Q equals I, then Q transpose must also be equal to the identity matrix. So there is another definition for an orthonormal matrix, which is the definition I'm going to use for stating this proposition. which is that a matrix A in R
Excuse
to
me,
the
sir.
yeah.
Sir, in above proof, BA we are taking not is equal to I.
Yeah.
So why am writing ABA is equal to A?
AB is equal to I, right? If AB equals I, that's what we are trying to show here. That if AB is I, then BA is not is must also be equal to I. So AB is equal to the identity matrix. Identity times A is always equal to A, whatever A is.
Yes, sir, I got it. Thank you.
Sir,
Yeah.
I have a doubt. So
Yeah.
on the top, you have written Q transpose Q equals QQ transpose equal to identity matrix. But the
Yeah.
dimension of Q transpose Q will not be equal to the dimension of QQ transpose, right?
Square.
Oh, okay. It's for n cross n. Okay, fine. Okay. If it is, suppose if it's in rectangular matrix, then how will this?
Then it's no longer true that if Q transpose Q is I, then QQ transpose must be equal to I.
Okay. But either of them will hold true, right? Like at least, I
So,
mean, if one doesn't hold true, then the other will definitely hold true, right? In case it's an orthogonal matrix.
so if the columns are orthonormal, then Q transpose Q will contain as its entries inner products between columns. Okay, and so that will be equal to the identity matrix. But QQ transpose need not be the identity matrix.
Okay.
Similarly, if the rows are orthonormal, then QQ transpose will be the identity matrix, but Q transpose Q need not be the identity matrix.
Okay, fine. Okay, sir. Yeah.
So this is said to be an orthonormal matrix if it preserves the inner product. So what I mean by that is, if I take the inner product between AX and AY, that is equal to the inner product between X and Y for every X and Y belonging to R to the N. Okay, so that's also another definition of an orthonormal matrix. Okay, so here is the proposition. So the following statements are equivalent. A is, so here A is a matrix in R to the N cross N. B is A preserves the length. By that I mean AV for every V in R to the N. So recall Okay, that's the definition of the V. In fact, for the moment, I won't write the subscript 2 because this result is actually more general. It doesn't require the inner product to be defined the way we have been defining it until now. We've seen only one example of an inner product. There are other possible definitions for the inner product, but right now we are working with the dot product as the notion of the inner product, but any other valid notion of the inner product can be used to define a norm defined like this. Okay, and that is called a norm that is induced by an inner product, and this is true for any definition, any valid definition of an inner product. Okay, so, points.
Sir, can you explain the previous definition? Ax, Ay equal to xy. What is Ax? It is the column.
Yeah, x is a vector, so Ax is a vector. So it's looking at the inner product between Ax and Ay.
Okay, so what is x and y? It is numbers or vectors?
It's right here. Xy belongs to R to the n.
So if it's the column 1 and column 2, it will be 1 and 2.
What do you mean? X is a vector in R to the n. Y is a vector in R to the n.
Okay.
X and Y are vectors. X is a vector and Y is a vector. So if you compute the inner product between X and Y, whatever number you get is the same number as what you would get if you computed the inner product between Ax and Ay. And that's true for any pair of vectors I choose.
Okay.
I think this is important that everybody understands the definition, otherwise this entire proposition makes no sense. So if you have other questions about the definition of an orthonormal matrix, please ask. The definition is that it should preserve the inner product. That is, you take two vectors in R to the n. If you find their inner product, that is xy, and then you take Ax and Ay, those are also two vectors in R to the n, and you find their inner product. And those two numbers must be equal for all pairs of vectors in R to the n, not for just one particular pair.
Sir.
Yeah, go ahead.
Sir, actually, in that inner product line, is a matrix into a vector is actually a transformation, right?
Yes.
So what is the meaning? I mean, inner product is actually the length, I mean, the component of x along y or something in that sense, right? I mean, inner product between x and y means the component of x along y.
Correct.
So,
it's preserving those. It's preserving the relative orientations of x and y. That is what it means.
Okay, in whatever frame we transform these vectors.
Yes. Yes.
Okay.
So, if for example x and y were orthogonal, they were perpendicular. Transformation by A, they will remain perpendicular to each other. Are collinear with each other, then even after transformation by A, they will remain collinear with each other. That's what it means.
Okay. Okay.
And mathematically, this is the precise meaning of a matrix being an orthonormal matrix. It preserves all inner products, not just when x and y are orthogonal or not just when they are collinear.
Thank you, sir.
Hello, sir. So just a question, like it is not when multiplied a vector with A, it's not changing the length. So is it will rotate the vector?
Yeah, that's a good way to think about it. It will rotate the vector, but it will not change its length. So in some say, so another way to put it is that every rotation matrix is actually an orthonormal matrix. Okay. And every orthonormal matrix can be thought of as a rotation matrix.
Okay.
Sir, is this sometimes called orthogonal matrix as well?
Yeah, so That's actually a good point. Depending on the textbook you refer, some textbooks refer to this kind of matrix as an orthogonal matrix. Some textbooks refer to it as an orthonormal matrix. I prefer the terminology of orthonormal matrix because it also clearly tells you that every column is unit norm. An orthogonal matrix, if you really wanted a more general definition, it is a matrix where the columns need not be unit norm, but they are still orthogonal to each other. Okay, that could be a more general definition of an orthogonal matrix. Yeah, just to be clear, I want to call it an orthonormal matrix in this course, and it's a matrix whose columns are unit norm and are orthogonal to each other.
Sure, sir.
These are two equivalent definitions, but for the purposes of showing this proposition, I will go with this definition, meaning that it's an orthonormal matrix if it preserves the inner product. So the third property is that A transpose is equal to A inverse. A is an invertible matrix, which means that A transpose A equals A transpose, which equals the identity matrix. And the fourth property is that the rows of A form an orthonormal basis for R to the n. And the last one is that the columns also form an orthonormal basis for R to the n. Okay, so how do you prove such a proposition? So it says that these statements are equivalent, meaning that if I tell you that A is orthonormal, it's the same as me telling you that A preserves length. So if you have 5 statements like this, the way to show that all of these are equivalent is to say, for example, you take the first 2 statements, you should show that A implies B and B implies A. That means A and B are equivalent. Then you take, say, the third statement, C. Then what you have to show is that either A or B, one of those 2 statements implies C, and C implies either A or B, one of those 2 statements. Then it means that A, B, and C are equivalent. Then similarly, you take D and you show that D implies one of these 3 statements, A, B, or C, and you should show also that A, B, or C, one of these 3 statements implies D, and so on. If you show all of that, then you've shown that these statements are all equivalent. Of course, there are many ways to do it. For example, you show A implies B and B implies A. Then you show B implies C and C implies B. Then you show C implies D and D implies C and D implies E and E implies D. So that also means that these statements are all equivalent. So let's see how to show this. So first we'll tackle A implies B. So we want to show that if A is an orthonormal matrix, then it preserves the length, meaning that for any vector, if I look at the length of V, it's equal to the length of the transformed version of V, which is AV. So and vice versa. Okay, if A preserves length of every vector in R to the n, then A must be an orthonormal matrix. So to show first A implies B, an orthonormal matrix implies that it preserves the length. Then what I need to do is I just need to consider the inner product between AX and AX. And the inner product between AX and AX because A is an orthonormal matrix, by definition, it preserves inner products. So basically this is equal to the inner product between X and X. Okay, so that means that if so this is nothing but ax square, and this is nothing but x square, which means that ax equals x. So this means that so this is what we wanted to show, that A preserves length. So A implies B. Similarly, B implies A. What I need to do is I need to show that if A preserves the length, then A is an orthonormal matrix. That means that all inner products are unchanged by multiplication by A. So what I'll do is I'll consider, yeah.
So could you explain how inner product of AX with itself is equals to inner product of X with itself?
That's from the definition. So what I want to show here is that if A is orthonormal, then it preserves length. So if A is orthonormal, by definition, because it's an orthonormal matrix, it preserves the inner product. The inner product between any two vectors. In fact, y need not be equal to x. So if A is an orthonormal matrix, then AX, AY is equal to the inner product between x and y. This is true for all pairs of vectors x and y. And so all I'm doing is to take a special case of this where y equals x. So the inner product between AX and AX is equal to the inner product between x and x. So you can see that although the statements look quite different from each other, saying that A is an orthonormal matrix, meaning that it preserves inner products, and saying that A preserves length, they seem different from each other in terms of statements, but in fact it follows trivially from the definition. Is it clear?
Yes, sir. Thank you, sir.
So if I take the inner product between ax plus y and ax plus y, this because A preserves length. So now I want to show that B implies A. So A preserves length. So this is nothing but the length of A times x plus y square. And so this must be equal to the length of x plus y square. But if I expand this out by using the linearity of inner products, then this thing can be written like this. It's the inner product between ax and ax plus 2 times the inner product between ax and ay plus the inner product between ay and ay. And the right hand side, if I expand this out, I get the inner product of x with itself plus 2 times the inner product between x and y plus the inner product between y and y. Now once again I use the property that A preserves length. So this quantity, inner product between AX and AX, this is equal to the inner product between x and x. And this term is equal to the inner product between y and y. So this xx will cancel with this xx, this yy cancels with this yy, and the 2 and 2 can cancel, and so you're left with ax ay equals xy. So it preserves inner products, and so then it is orthonormal. Then we consider C, the statement C. So,
Sir.
yeah.
Sir, the moment you are considering inner product of ax comma ax is x comma x, so that moment only you are considering it to be orthogonal, right? Orthonormal, right?
That is
Otherwise,
what
how?
we're showing here actually.
Yeah, but
So,
in the second last step, you already considered ax comma ax is x comma x.
so what we are trying to show here Okay, I think it's important to pay attention a little bit to what we want to show. So what we want to show is that B implies A. What is that? It is that if A preserves the length, that is, if norm of AV equals norm of V for every V in R to the N, then A preserves the inner product, that is, the inner product between AX and AY is equal to the inner product between X and Y for all XY in R to the N. That is what we want to show. And that's what we're doing here. It's not a difficult proof. It's very simple, but it's good to keep in mind exactly what it is that we are showing. So in writing the first step, I'm using the fact that B is true. I'm saying if B is true, then I want to show that A will preserve an inner product between any pair of vectors. So this is true because A preserves the length. This is also true because A preserves the length. AX equals X comma X. That's also true because A preserves the length. And similarly, AY equals YY is because A preserves the length. And a consequence of this is that I'm getting AX/AY inner product is equal to the inner product between X and Y, which means that A is orthonormal.
Sir?
Yeah.
Sir, so you gave the definition that an orthonormal, A is an orthonormal matrix if it preserves the inner product. But that statement does not speak about the converse. That is, if it preserves the inner product, then it should be orthonormal. That part is not implied by the definition, right?
Yeah. So so this is also a very good point. In mathematics, a definition is always an if and only if statement. Okay. So we write it like this. A matrix is said to be an orthonormal matrix if it preserves the inner product. But when we are saying that it is said to be or it is defined as an orthonormal matrix, we mean that this is an if and only if condition.
Okay. Okay.
Okay. By definition, an orthonormal matrix is one which preserves the inner product. All definitions in mathematics are like this. We define something to be in a particular way. It means that A is equivalent to B. If I define A to be equal to B, or A to be, or if I say a matrix A is defined to have a property X, if it satisfies Y, it means that X and Y are equivalent to each other. Okay, now let's do the next step. Next, if I consider the inner product between AX and Y, I'll make a statement. This is equal to the inner product between X and A transpose Y. This can be seen by just writing out the expansion of what this will be. So basically this AXY is nothing but summation I equals 1 to n, sigma j equals 1 to n, aij, xi, and yj. And if you expand this out in terms of the entries of A, you will find that this is also exactly the summation. So I should say okay. So now what I can do is instead of y, I will replace y with ay. Then what happens is that I get, so I should write that out so we don't have confusion later. Then what I get is the inner product between AX and AY. Now, because so suppose A is an orthonormal matrix, then it preserves inner products. So that means that this is equal to XY. and this is equal to the inner product between X and A transpose A times Y. And this is true for every X, Y. So if A is orthonormal, then we have that this is equal to this for every X, Y in R to the N. So then that means that what I can do is I can take example vectors for X and Y. X equal to EI, the ith column of the identity matrix, and Y equal to EJ, where EI equals the ith column of I n cross n. Then what I have is, if I consider the left hand side, this EI EJ, so EI EJ is equal to, I can write it as delta IJ, which is this equal to 1 if I equals j and 0 otherwise. Then the right hand side is the inner product between EI and A transpose A EJ, which basically, if you expand this out, you will see that this exactly pulls out the ijth entry of A transpose A. So that means that the ijth entry of A transpose A is delta ij. Which means that A transpose A is the identity matrix. So then it means that A transpose is the inverse of A. And A implies C. So we've shown that. Now, conversely, if A transpose A is equal to the identity matrix, then if I consider the inner product between X and A transpose AY, this is equal to, this is the identity matrix. So this is always equal to X and Y, the inner product. Okay, because A transpose A doesn't change Y at all. But then the left hand side, this I can move this A transpose over here, and I can, so more generally, so let me just write it like this: X A transpose times AY. I'll consider this to be some vector. A transpose times something is equal to the inner product between AX and AY. And so thus AX AY equals XY for all XY in R to the N, and thus C implies A. Okay, and the last step is just that if A transpose equals I, it means that the rows of A are orthonormal. So we've seen that yeah, so these two are equivalent statements, because this is just computing the inner product between rows of A, And if this is equal to I, it means if I take any pair of any distinct pair of rows, they are orthogonal to each other. And if I take any row, it has unit inner product with itself. So the rows of A are orthonormal. They are both equivalent statements. And so C implies D and D implies C. And similarly, A transpose A equals I is the same as saying that the columns of A are orthonormal.
Sir?
Yes.
Sir, in order to show that inner product of Ax and Y is same as inner product of X and A transpose Y, can we use this formulation that inner product of X, Y is same as X transpose Y?
Yeah, it's
And
the same point. Yeah,
we
it's
can
exactly the
separate.
same. Yeah, it's
Yes,
exactly
sir.
the
Then
same
we can
point.
separate it. Okay.
This is it. This is the point.
So because this summation sometimes does not click how to write in form of this two summations, but directly doing the transpose we can easily separate it out.
Yeah. So, but that will be valid. Yeah. So you can do it that way also.
Okay. Okay, sir. Thank you.
No. So the thing is that it follows from the definition of the inner product that we said. So it's you have to take the transpose of the first vector and then multiply it with the second vector.
Yes.
And so if you think of it that way, it follows immediately. That's also a valid way to write it out. Okay. Any other questions?
Sir, is that true for all A? No, right?
Of course. This is
Okay.
always true.
Okay.
Ax comma y inner product is always equal to x comma A transpose y. What the previous student just said is that if I think of x, y to be equal to y transpose x, if I think of it this way, which is how I defined the usual inner product earlier, then if I were to take Ax and y, this is equal to y transpose Ax, which is also equal to A transpose y whole transpose times x,
Yeah, I got it.
and which I can write as x transpose times A transpose y. No, I don't need to do that.
So, so here to prove the equivalence of 5 statements, we are actually going through 10 proofs, but actually 6 proofs would suffice, right? Because A implies B, B implies C, C implies D, D implies E, then E implies A, then all of them will imply each other.
Yeah.
So
that's also a valid way to show it. There are many ways to write out this proof. I've shown you one way here. Okay, so if there are no further questions, look out for your assignment at.
Excuse me, sir.
Yeah.
I have one question. So in the statement 4.